Next speaker is Mina Aganagic from UC Berkeley. She'll tell us about categorification of Chern-Simons link invariants and progression.
Okay, I'm really happy to be here to help celebrate curiosity. And of course, Caltech is my alma mater. So I'll tell you about 3 papers that appear over the last 3 years and many work in progress. So for many decades, curiosity has been a central person in our field. And so his discoveries have certainly inspired my research many times. And this talk I'll tell will build on at least 2 of them. In '84, Von Jones discovered a polynomial link invariant depending on 1 variable. The Jones polynomial is defined by picking up a planar projection of the node and a skein relation that it satisfies as you untie the node, where here you'll take n is equal to 2 to get the Jones polynomial. It turned out that other values of n also give notch invariance. In particular, setting n is equal to 0, you get the Alexander polynomial, which is the first known polynomial link invariant that actually dates back to 1928. Now it works. So the proper framework for these invariants was found by Edward Witten, who showed that they originate from Chern-Simons theory, a topological quantum field theory in 3 dimensions. So Chern-Simons theory is a rare example of a quantum field theory that in dimensions bigger than 2 that we can explicitly solve. So in particular, Witten showed that Jones polynomial comes from Chern-Simons theory based on Lie algebra SU2 with knots colored by its spin-Hawk representation. The Alexander polynomial comes from the same setting by taking the Lie algebra to be the Lie superalgebra GL1/1.
Is it not working? Sorry. Okay, maybe I should have. Okay, the students have interfered. Okay, it's not working. Okay, so somehow. Yeah, somehow. Sorry, it doesn't want to be hidden. Okay, so let's keep it open. It's a little bit annoying, but I think it's. Yeah, I can move it. Yes. Yeah, there is option of hiding, but yeah, but when you hide it, it interferes. But okay, let's keep it open. Is it working now? Yes.
No.
No. Oh, okay, it's not working. Okay, I don't know why. Let me just. Sorry about that. Yeah, let me just share again. Yes. Yes, it is working. Okay, let's keep it open there.
So it displays the Alexander polynomial and the Jones polynomial in a more general framework, which you get by considering Chern-Simons theory based on different Lie algebras and varying representations coloring the knot. In '98, Kavanagh showed that one can that there's a deeper structure underlying Chern-Simons theory. He showed that one can associate to a link a collection of bigraded vector spaces whose equivariant Euler characteristic is the Jones polynomial. Kavanagh's homology groups are graded by the Fermion number and by an additional equivariant grading associated with Q, and they turn out to be themselves link invariants, independent of the link projection used to define it. Kavanagh's construction is part of the categorification program pioneered by Crane and Franklin. So it's good to keep in mind the simple toy model of categorification, which comes from taking n to be a Riemannian manifold whose Euler characteristic is categorified by the cohomology groups of M, which you get as the cohomologies of the Durand complex. From physics perspective, the Euler characteristic is the partition function of supersymmetric quantum mechanics with a manifold M as a target space. The collection of vector spaces that you need to construct homology groups is provided by our supersymmetric ground states, is provided by Morse theory approach to supersymmetric quantum mechanics. The vector spaces are the spaces of perturbative supersymmetric ground states indexed by the Fermion number. The action of the supercharged Q on this complex is generated by infinite. Kavanagh's categorification of the Jones polynomial is completely explicit and easily calculable. In 2013, Ben Webster showed that abstractly, there exists a categorification for general Lie algebra that's based on what are known as KLR double algebra, generalizing algebra that appeared in works of Povanov, Lauda, Requiem, and Webster. However, Webster's construction is completely formal. There's nothing whatsoever you can calculate in it. So despite, still, constructions are remarkable. They say that, there's a deeper theoretical and Simons theory. However, the way they come out of mathematics, you're missing a fundamental principle, which explains why such a thing is possible. It really doesn't have any right to exist. Because unlike in our toy example of categorification of the other characteristic of a Riemannian manifold, Povanov's construction and its generalizations don't come from geometry or physics, certainly not in any unified way. There are connections to both geometry and physics, but not in a completely unified way. So the problem Povanov initiated is to find a general framework for construction of linked homology groups that work uniformly for all Lie algebras that explains what linked homology groups are and why they exist. In fact, there is a single setting where mathematicians did find a theory that does come from geometry and explains and physics and explains what at least what linked homology groups are, why they're a homology theory. That setting corresponds to the theory categorifying the Alexander polynomial, and it's known as Heger-Floer theory. Heger-Floer theory is essentially a topological A model. So despite the fact that the Jones and the Alexander polynomial are defined by merely the same scalar relation, which exchange the value of the integer, the theories that categorify them are nothing alike. The categorification of the Jones polynomial comes from algebra, while that of the Alexander polynomial from geometry. So the solution to the knot categorification problem turns out to come from mirror symmetry. Mirror symmetry is a reality that's covered by aspect theorists. Today, it is largely a subject of mathematics, not so much of physics anymore. And in mathematics, it connects two large areas that are known as algebraic and symplectic geometry. Homological mirror symmetry describes how mirror symmetry acts on rings. And it turns out, naturally, it gives rise to a host of homological invariants of a geometric origin, the kind you'd want for knot categorification. However, most of the time, the invariants you get from homological mirror symmetry are not interesting at all outside of the narrow setting at hand. For example, if you study homological mirror symmetry for the quintic, all you'll understand is the quintic. So it turns out that there's a vast family of mirror pairs manifolds where homological mirror symmetry does lead to interesting invariants and leads to the solution to the knot categorification problem. Many special features will exist in this family, one of which is the fact that it will involve hyperkähler manifolds. This will translate to the fact that problems, which even in the world of homological mirror symmetry typically have only formal solutions, will actually be solvable explicitly. So this is sort of an analog of the fact that Chern-Simons theory is a quantum field theory which we can solve explicitly. It turns out that the theory underlying it is equally explicitly solvable. So one of the sides of mirror symmetry will turn out to be a theory that generalizes Heger-Floer theory from Lie 1 + 1 to an arbitrary Lie algebra, in fact, Lie superalgebra. So, in this talk, I'll describe that I'll assume that our Lie algebra is simply Lie. There's a generalization and an order of the algebra. There is a generalization to non-simply Lie algebra, then also Lie superalgebra, which go along the same lines, but differ in some aspects, technical. So, mirror symmetry is, of course, a story about two-dimensional physics. And the reason two-dimensional physics matters is that the descriptions that we'll get come from two-dimensional theories associated with length times time in a theory as embedded in R3 times time. In fact, more precisely, as it comes out of string theory, the theory is naturally expected to describe lengths in R2 times S1, not just in R3. So the two-dimensional theories we'll be talking about are the ones that live on defects of a 6-dimensional 0-2 conformal field theory, as was anticipated from the work of Hiroshi with Bapa in 1999, and also Gukov, Schwartz, and Bapa a little bit later. Superstring theory, however, we will not feature further in solve because the solution, just as the problem itself, doesn't require string theory to pose it. Once you've understood how to solve it, you also don't need string theory to phrase the answer. However, string theory sort of targets for us with no ambiguities whatsoever along the way. So the starting point, if you want, is Hiroshi's work with Bapa in 1999. The final answer is what I'll tell you about today. I've described the path between them elsewhere, but today I'll just focus on the answer. Now, our starting point will be a fact described by Whitman in his same 89 paper on the Jost polynomial, which is that underlying consignment theory is a 2-dimensional conformal field theory associated to D and the consignment level kappa. The double is the W model, which has a finally algebra symmetry. The Hilbert space of Chern-Simons theory on a Riemann surface function of Wilson line is a space of conformal blocks of the finally algebra. Every conformal block, and hence every state in the Hilbert space, arrives with a solution to a famous linear differential equation, which was discovered by Knižničan and Zamolodchikov in 1984. The variables in the equations are positions of punctures on a Riemann surface. By varying the positions of punctures in Chern-Simons time, you get a quadratic rate. You also get a monodromy problem, which is to describe an analytic transformation of the solutions of the equation along the Cartan parameter space corresponding to the break. Typically, such problems are hard. In Chern-Simons context, it was solved by Drinfeld and Kovlin and Lustig, who showed that monodromy matrices of the KZ equation are computed by quantum group R matrices associated to G. These R matrices describe exchanging neighboring pairs of functions. You can get any link invariant as a matrix element of the gradient matrix between conformal blocks corresponding to class. Such conformal blocks are obtained by bringing together pairs of punctures followed by complex conjugate representation and letting them disappear. So both gradient and fusion in conformal field theory play an important role in getting those invariants. So to categorify quantum link invariants, you'd like to associate the space of conformal blocks you get at a fixed time slice a bigraded category, which in addition to the usual fermion number gradient has a gradient associated to Q. To grade, you'd like to associate functors between categories at the top and the bottom. To links, you'd like to associate a vector space whose elements are morphisms between the objects of the category at the top and the bottom up to the action gradient. And you'd like to do all that so that if you take the trace of the resulting vector spaces or the characteristic, you get quantum invariants. So typically, people proceeds by coming up with some category, and then you have to prove that the categorification gives you the quantum, what you want to categorify. So in the solution I'll describe, the second step is automatic. That you get for free. So mirror symmetry relates pairs of Calabi-Yama manifolds exchanging variations of complex or B-type and symplectic or scalar structures, A-type structures. These names are inherited from the topological B and A model, whose moduli dissolve. So D-branes are key objects in string theory, and it turned out that thinking about how mirror symmetry acts on D-branes led to deep insights into mirror symmetry. One such insight was due to Strominger and Zafel, who showed that in order for every spotlight brane X to have a mirror on Y, mirror manifolds have to be fibered by T-dual tori, and in fact, mirror symmetry must be T-dual. You can regard branes on a Calabi-Yama manifold as objects of a category whose morphisms are open strings stretching between branes. There are in fact two natural categories depending on which kind of supersymmetry the branes preserve, A or B type, and world. the corresponding morphism spaces are cohomology groups of the supercharges preserved by the brain. Both have well understood and much studied mathematical formulation. The category of B brains has objects which are brains supported in complex and manifold of X. It has a precise mathematical formulation, and which goes under a pretty terrible name of the derived category of coherent sheaves. But what they are just B-type brains. And the whole structure of derived categories is what you need to describe what we physicists mean like as a brain and its behavior. The category of A brain comes from symplectic geometry. It's known as derived supply category. And its objects are brains supported on real or Lagrangian submanifolds. A homological mirror symmetry is an equivalent of the categories. It says that for any pair of B brains on X, there's a mirror pair of A brains on Y, such that morphism spaces between them agree. The space of supersymmetric ground states between them agrees. So mirror symmetry naturally provides a supply of categories of geometric origin. The spaces of supersymmetric ground states for A brains categorify, for example, the intersection numbers of Lagrangians. And however, not only does it provide a supply of categories, it turns out that in an appropriate setting, it solves the knot categorification problem. And in parallel to solving the problem, we'll discover a new family of pairs of mirror pairs, which come from in physics, if you want, of supersymmetric gauge theory, which turn out to be connected to representation theory. And moreover, where homological mirror symmetry is as explicit, can be made as explicit as in the very simplest known examples. So if you want, we will land on a dream world for mirror symmetry, the kind that people did not have when they wrote this very big book on B brains and mirror symmetry. So Canisian's homological equation, which plays a central role in knot theory, turns out to have a geometric counterpart. In the world of mirror symmetries, there's an equally fundamental differential equation, which is sometimes called the quantum differential equation. I remind you, essentially starting with the Canisian homological equation, you could have discovered everything we know about Chern-Simons link invariants. Okay. So this quantum differential equation is a linear differential equation for a vector value function on the modular space of either A or B type structures. So either complex vectorial modulo of X or complex structures as well. The name comes from the A model, where the connection in this equation is a connection of vector bundles with fibers, even for homology groups, where the connection itself is defined using the A model, using the quantum product of the homology that A model of revision theory provides. Now, in the mirror, the connection comes from classical geometry. It's called the classical Gauss-Minen connection on mid-dimensional homology, where so from perspective of X, the solution to the equation is obtained as a partition function of H with the sigma model on a very, very long cigar with a circle boundary infinity. You get a specific solution to the equation by choosing a B-type boundary condition at infinity. Because our cigar is infinitely long, we are allowed to mix A-type twist in the interior with a B-type boundary condition at infinity. And the solution you get depends only on the charge of the brain, not on the details of what the brain is. So the fact that solution to the equation makes A and B type structures is a hallmark of central charge functions, which these the actual solutions mildly generalize. They generalize by placing some insertions at the table. So both this equation and its monotropic problem featured prominently studied in the very first papers on mirror symmetry. These were, this is, if you want, one way of writing the Picard-Fuchs equation that that appeared in Candelas and Delos, the paper on mirror symmetry. So the equation not only has the flavor as its quantum differential equation, but under certain conditions, they simply coincide. On the knot theory side, you want to take the Riemann surface to be an infinite convex cylinder rather than a complex plane of function. So this will allow us to describe links in R2 plus 1, not just in R3. And we'll also specialize the real algebra to be simply. On the geometric side, we'll take our target space to be a very special Calabi-Yau manifold, which you can think of as the moduli space of D manifolds on R3, with prescribed singularity. So that's a singular manifold there. The manifold group is related to Chern-Simons gauge group by Langlands or electromagnetic duality as in Chern-Simons theory, those do not therefore in three-dimensional space as cause of heavy particles electrically charged under LG. And in the geometric description, the same heavy particles are Dirac manifolds of the Langlands dual group. The fact that electromagnetic duality is what's needed to understand categorification was anticipated by Wood. So this manifold played a role in mathematics before for its connection to S-duality and Langlands. The same manifold is best known to us, perhaps, as the Coulomb branch of a certain three-dimensional quiver gauge theory with n equals to 4 supersymmetry. So, but for now, we'll think about it as a monopole moduli space. The monopole moduli space is parameterized by positions of smooth two positive type monopoles on R3, where we keep the positions of singular monopoles fixed. The singular monopoles tell us where to not go, and they also determine the matter. So we'll split R3 into R times C, and so positions of singular monopoles in R are the real Taylor moduli, while positions of C are the complex structure moduli. So the monopole moduli space has more symmetry than your typical Calabi-Yau because it's hyperkähler. So as a consequence, exponent homology is trivial unless you work at invariants with respect to force action that scales this homomorphic symplectic form with base Q, and which breaks their hyperkähler symmetry. That symmetry comes from rotation of the extra complex plane, and it's an isometry of X if you put all the singular monopoles on ideal. So the parameter Q of knot theory will be related to keeping track of charges of states on the symmetry. So the fact that the KZ equation in sector form is the quantum differential equation of X, our monopole moduli space, or the Coulomb branch of the 3D anti-control theory, is a theorem by Ivan Danilenko, who is a postdoc at Berkeley. We were forced to take the Riemann surface to be an infinite cylinder rather than a plane because of a string effect. It's because the details that pair the real Kähler moduli to get a complexified one a priori. So it follows that which solution of the KZ equation you get is determined by a choice of a B-type ring as a boundary condition at affinity. And it also follows that a braid has a geometric interpretation as a path in moduli space of X that avoids singularity in Kähler moduli. So a sample expectation in mirror symmetry is the fact that along a path in complexified Kähler moduli space that avoids singularities, your brains may change, but the category of B-type brain stays the same. You get an equivalence of the category before. So the reason this is true is as follows. So physically, the brain group acts in the signal model and cigar by letting the module of the theory vary near the boundary infinity, where the direction along the Euclidean cigar coincides with the direction along the braid, and it coincides with Chern-Simons time. So it follows that a signal model on an analysis with moduli that vary according to the braid gives you a monogamy matrix elements of the KZ equation between a pair of brains boundaries. And for all this, you view topology along the angle. Yeah. So the category of brains manifestly categorized by matrix elements between pairs of conformal blocks. The reason it does so is that the signal model on the same Euclidean analysis, where instead you do the time as running around the circle, computes the supertrait, which is the other characteristic of the supercharge preserved by the homology of the supercharge preserved by the pair of rings. That homology of the supercharge is the basic ingredient in the category of rings, the the vector space or the space of more than green. So for any pair of branes, we get homology groups whose other characteristic is the gradient matrix subgroup. So to extend to invariants, you'd like to find objects in the category of branes that lead to conformal blocks in which pairs of vertex operators fuse to trivial representation. So for this, you'll need to understand the geometric interpretation of fusion in the category of branes. In conformal field theory, as discovered by Cyber and Moore, fusion diagonal is gradient. The analog of this in the category of branes turns out to be, you can't quite diagonalize the action of grading on category of branes because grading tends to mix them up and mix them up in even a simple example. So the next best thing is some characterization on a category that was written by mathematicians in abstract terms as a rough structure to describe the action of grading in this category. And here, the action matrix is split. And you learn from this that the caps and hooks come from branes that have a very simple geometric meaning that simply vanish in cycles in line. Okay, so vanishing cycles that vanish as the brane pair once together. Pairs of functions together. And so using very special properties of these filtrations, which let you explicitly describe the action of grading on the category, I proved that homology groups not only categorify the corresponding invariants, but that they are themselves invariant. The fact that they categorify them is manifest. The fact that they are actual link invariants, the vector spaces themselves are link invariants, is something you have to prove, and you can do it. So this approach explains the origin of homological link invariants and geometry and physics in a manner that works uniformly for all groups. Recently, I've actually proved that link invariants, they come in beta and X, are in fact equivalent to the algebraic invariants he defined in 2013, and in fact generalized them to links in our group number one. So we took some time in the beginning. I'll just need a few minutes to explain this match. Okay. Now, so here I'll explain just how to develop the sum in the picture. Eventually, to give an explicit solution of the theory, we'll need to make use of mirror symmetry. Okay. Now, in the very best instances of homological mirror symmetry, mathematicians have learned how to make the equivalence of the two categories match. They learned how to make mirror symmetry match, but in a very simple example. What will turn out to be the story here is that we can generalize this very simple example to this class of manifolds, which are far more non-trivial than what they know. But anyway, once you learn how to make mirror symmetry manifest, then descriptions of these otherwise very abstract categories becomes concrete. Okay, and you can actually solve it here. So one of the simplest examples of homological mirror symmetry is when you take your X and Y to simply be a pair of infinite cylinders. Okay. Where the base of the vibration is just a real line, and the torus side is a circle. So both X and Y are simply cylinders. The category of brane on the two sides turn out to be both generated by a single brane. From one brane, you can build any other. Okay. That brane on the side of X is simply a D2 brane that's supported on the whole complex cylinder. On the mirror, it's a D1 brane that runs along the cylinder. Now, these branes look different, but it turns out that the algebra of open strings is the same. Okay. The algebra of open strings is the same, and it's simply equal to the algebra of functions in the complex cylinder. On the B branes and X, that's simply to show. On the side of the A branes, you have to do some work to show that the algebra of open strings is just the algebra of functions in the complex cylinder. So the homological mirror symmetry is actually a consequence of a pair of equivalents, where the category of branes on X and the category of branes on Y are equal because they're both equal to category representation of the open string algebra. And the open string algebra is simply the same on the nodes. Okay. So this is the simple example of the model of how you hope to understand mirror symmetry in all cases. And as far as what's known, this is pretty much this kind of cylinder example, or maybe when a target is a disk, is what mathematicians knew. Okay. So it turns out that Webster's proof of equivalence of his link invariance by B category and by his scale and W algebra is really the first of two equivalences in homological mirror symmetry. Now this side is completely still knowing this. Descriptions of these categories are completely abstract. What A-rings allow us to do is to get an explicit geometric understanding of the category, and actually so it turns out that this homological mirror symmetry is the most naive generalization of the simplest example I just gave. Okay, the underlying manifolds are product of cylinders, where in fact you can read off everything from a single cylinder and actually solve both theories, and actually turn the theory into something where with mirrors of Rastav and Massoud and Aliza now, we have computer mathematical programs that compute link homologies for small algebras right now, and then in principle there's an algorithm that works uniformly for any superalgebra. So it turned an otherwise thanks to mirror symmetry, an otherwise abstract object is completely concrete, and in fact as solvable as original Chern-Simons. Thank you.
Yeah. So probably you explained it, I just missed it. So your construction depends on how to present the node as a series of monodromy transformation. And so the categorization you get out of this process is it invariant, and how you refer, because given nodes can have a variety of different monodromy.
Yeah. So on the B side, it's something you can prove, and this is what I described. Okay. On the A side, the fact that it's much easier to understand in terms of Lagrange and how great it is. But still, to prove that you actually get link invariance, you can say you add clause and mirror symmetry, or there's some special moves you have to prove. Again, that you actually get. There are only two.
So the vector space you got out of this, themselves are invariant.
They themselves are invariant.
Thank you.
And moreover, you can actually compute them explicitly. So we know how to explicitly give you the space of supersymmetric ground.
Thank you.
The simple advantage of your computation looks like what's happening right at the category generated by the brain.
Yes.
Is that happening here or is it something?
The category here is generated by a finite set of brains. Okay. These brains turns out that on the A side, so they're both generated by a finite set of brains. On the A side, these brains are symbols of some lambda Gilbert potential. Okay. You can spell out explicitly what they are, and you can explicitly compute the algebra of constraints. Okay. And there's a finite number of them. Moreover, we know how to do, and this is in general a problem that in the world of mirror symmetry people don't know how to do. Is if I give you a picture of the brain, I know how to describe it in terms of generator, which is what allows you to actually do calculations.
Let's thank you, Mina, for